Okay, so we're starting experiment 6 about thermodynamics, and today we are going to talk about the Prelab. So the first question says define delta H for the reaction. This is something that you should already have in your notes, and you've seen it in the textbook, so go back and find it. It's also in the beginning of in the introduction to the lab. So you can find the definition there. Just make sure you understand what it is the point. Number 2, define specific heat. Same idea. You've encountered it in the notes. You've encountered it in the textbook. So one of those two places you want to go back and define that. So we're going to start with number 3. And you have a PDF of this on our classroom site, but I'll read it to you. The specific heat of a solution is 4.18 joules per gram degree Celsius, and its density is 1.02 grams per milliliter. The solution is formed by combining 25.0 milliliters of solution A with 25.0 milliliters of solution B, with each solution initially at 21.4 degrees Celsius. The final temperature of the combined solutions is 25.3 degrees Celsius. Calculate the heat of reaction, Q reaction, assuming no heat loss to the calorimeter. Use correct significant figures. So here's the data they give us for number 3. The specific heat of the solution, specific heat is C, 4.18 joules per gram degree Celsius. The density of the solution, 1.02 grams per milliliter. So it's a little bit higher in mass than pure water, and that's because it's got something dissolved in it. Those are the things that are going to react. In this case, you have A and you have B. Those are whatever compounds are dissolved in the water. Both of these solutions are initially at the same temperature, 21.4 degrees Celsius. So probably what happened is that they left these two solutions on the counter overnight and let them come to temperature with the room. This is probably the temperature of the room. This is pretty typical. 20, 21, 22 Celsius, typical room temperatures. Here's what's going to happen. When we combine them, we will now have 50 milliliters of solution. And when we combine these two things, if nothing happened, we would expect the temperature to remain the same. And so the initial temperatures here, we're going to keep for the initial temperature of this reaction. But we're told that the temperature, once the reaction happens, is at 25.3 degrees Celsius. So the temperature has gone up, and the solution would qualitatively be a little warmer. So we have some numbers here, quantitative data, temperature's gone up. So we want to know about the heat of the reaction, and so this is the formula we're going to use. Q, which is heat, equals mc delta T. Heat equals mass times the specific heat times the change in temperature. So let's look at the things we have. So going left to right, we want the mass of the solution, so the mass of all the water and the mass of the reactants. We don't know this exactly, but we do know volume and we do know density. Volume times density gives us mass, which is what we're looking for here. So we will have mass, we just have to work for it a little bit. Specific heat, 4.184 joules per gram degree Celsius. They gave it to us. And delta T is really T2 minus T1. And so we have that as well. And so we should be pretty well set to go ahead and start calculating Q. So I've already put in all the work here. So here's what's happening. We are looking at the mass of the solution, we're looking at the specific heat of the solution, and we're looking at the change in the temperature of the solution. What we've done is measure the water. And so we have to keep in mind that when we are putting a thermometer into an aqueous reaction, we're really measuring the water. We're not measuring the reaction itself. And so when I say Q of the solution, this is the amount of heat that the water has either absorbed or released. So here is my mass. Remember, volume times density is mass. And so if you double check this, that's grams. There's your specific heat given to us in the question, and T2 minus T1. So I went ahead and simplified it. The mass of this solution is 51.0 grams. The delta T was positive, temperature went up by 3.9 degrees Celsius. And so as we go through this, Celsius cancels, grams cancels, and that leaves us with capital J, joules. Joules is a measure of energy. Heat is a type of energy, and so we're measuring it in terms of joules. So here's what we're looking at. We are looking at how much heat the solution absorbed. The solution absorbed this much from the reaction. The solution absorbed this much heat from the reaction. And this positive sign tells us that we have absorbed energy. The solution has absorbed energy. We want to know about the Q for the reaction. How much heat did the reaction produce or absorb? And so this is the work from the previous page. I just moved it up. Draw a line here. So here's what happened. We found the amount of heat that the water or the solution absorbed from the reaction. We want to know the heat of the reaction, which is Q of the reaction. And so here's how it works. This is really a conservation of energy type idea. The heat of the reaction plus the heat of the solution is constant, so it's zero. But here's really where it applies to us. Q for the reaction, the heat of the reaction, is the opposite sign of the heat of the solution. So we already found Q for the solution. Here it is, positive 831. And so the Q of the reaction is just that number with the opposite sign. And so this is the amount of energy that is released by the reaction. Remember, negative means released. So I drew a little diagram of what could be happening here. So imagining that the reaction and the water are actually two different things. Simplified picture. So here's the reaction going on, and it is releasing energy. And then the solution is absorbing energy. So the solution was positive because it keeps getting energy added to it. And the reaction is negative because it keeps losing energy. It keeps giving energy away. You know, if you have $100 and you keep giving money away, the amount of money you have is decreasing like this, decreasing. So that's it for number 3. We found Q of the reaction, assuming that no heat was lost to the calorimeter, the container. But in number 4, we have some data that suggests we did lose some energy to the calorimeter. Think about it like this. If you have a coffee mug, just a regular porcelain type coffee mug, you put your coffee in there and you touch the side of the mug and it's actually pretty hot because the heat is leaving the coffee and going through the container and out into the environment. That's why coffee cools down quickly. So that container is losing a lot of heat energy. If you want to have something that keeps its heat energy for a long time, you want to get something like a thermos and something that will keep your coffee hot for a long time. You can tell if it's going to keep your coffee hot for a long time by feeling the sides. If the outside of the container is room temperature all the time, that's probably not giving off much heat through the container. But let's go ahead and read the question. In problem 3 above, the calorimeter has a heat capacity of 8.2 joules per degree Celsius. If a correction is included to account for the heat absorbed by the calorimeter, what is the heat of the reaction? So here's what they're telling us. The specific heat of the calorimeter is 8.20 joules per degree Celsius. So for every 1 degree change in temperature, this is how much energy is lost. And ours went up by 3.9 degrees Celsius. So if you figure we lost 8.20 joules per every 1 degree increase, we multiply these together. Q for the calorimeter is the change in temperature times C for the calorimeter, the specific heat of the calorimeter. And so we see that in this particular experiment, the calorimeter absorbed 32.0 joules. This was basically the coffee mug making itself or absorbing energy and becoming hot. So what is the Q for the reaction if the calorimeter absorbed 32.0 joules? And here's what it looks like. Here's your complete formula, and this one is another one that's listed in your lab. Q for the reaction is negative in sign to the total Q of the solution plus Q of the calorimeter. We have both these numbers. Q of the solution was positive 831. Q of the calorimeter was positive 32. Add them together, and it's opposite in sign. This is the Q for the reaction, negative 863 joules. So here's what's going on. The reaction actually released more heat than we measured in the solution because the container absorbed some of the heat. That's what's going on here. We measured the heat of the solution. We did not measure the heat of the calorimeter, so we didn't get an accurate picture of the reaction without this correction. And leading into number 5, if the reaction in question 3 is A plus B yields AB, and the molarity of A in solution A is 0.6 molar, and the molarity of B in solution B is 0.6 molar, calculate the enthalpy of reaction, that's delta H of the reaction, for the formation of 1 mole of AB in solution. Remember, delta H of reaction always has units of kilojoules per mole. So here's the reaction. A plus B yields AB. Molarity of A is 0.6. Molarity of B is 0.6. And we are looking for delta H of the reaction. And delta H of the reaction is Q of the reaction divided by moles of the reaction. So we have to know moles, which is what we're doing here. Volume times concentration tells us moles. we knew the volume of A, 25. We knew the volume of B was 25. They both have the same concentration. So we have this many moles of each of them. So here's what's going to happen. So this delta H of reaction is the heat of the reaction over the moles of reaction. So the heat of the reaction was negative 863 joules, and we have to change that into kilojoules. Those are the accepted units for delta H. And this is per moles of A, the way I calculate it. But we want it per moles of reaction. And so I had to do this step right here. So for every 1 mole of A, the reaction happens once. And when it's 1-to-1, you don't really have to write it down. But there are some reactions where you have coefficients, and it's going to be important for you to understand what's going on. So moles of A cancels out, and we end up with kilojoules per mole of reaction. And we see that it is negative 57.5 kilojoules per mole. This means that for every mole of A that reacts, or every mole of B that reacts, we are going to release 57.5 kilojoules. Quite a bit of energy